And we are live. Beautiful. So Hardy-Weinberg. Keep in mind there's two basic equations that we have to be able to work with. What are the two equations? P plus Q equals 1 is one of them, and P squared plus 2PQ plus Q squared equals 1. So if you don't know those, that's a problem. It'd be hard to actually do Hardy-Weinberg if you don't know the equations. Most importantly, if you don't know what these values represent, it makes it very difficult. Right? So again, P typically represents the dominant allele, Q typically represents the recessive. Or as we do with the sickle cell, they could represent the two different genes in a codominant or incomplete dominant situation. P squared represents homozygous dominant, two of the capital letter gene. 2PQ represents heterozygotes, and Q squared represents homorecessive. Okay? And if you have a dominant recessive situation, it's always easiest to solve for the recessive first. In this case, it says the allele Y occurs at a frequency of 0.8%. And that's for the allele Y, which is a lowercase y, which would indicate that as what gene? The recessive allele, which would be represented by what letter? Q. So in this case, they are telling us flat out that Q equals 0.8. They didn't say that was the homozygous recessives. They didn't say anything about the genotype. They're just flat out saying the Y allele is 0.8. The small y allele represents Q, so Q is 0.8. Well, so as I know that Q is 0.8, I can use the first equation to solve for P. Because P plus Q equals 1, I plug in P plus 0.8 equals 1, therefore P equals 0.2. Yes, no? Now, the question says, give the frequency of the following genotypes. Well, now that I know the frequency of the two genes, it's just plug in and do the math. So capital Y is homozygous dominant. Capital Y is homozygous dominant, which is represented by what value? P squared. So plug in for P. I now know P is 0.2 squared. 0.2 squared is going to be 0.04 or 4%. What's big Y, little y? That's represented by what value? Again, referring to the equation, that would be 2PQ. Again, plug your values in. So it'd be 2 times 0.2 times 0.8. And of course, if you do the math there, that's going to come out to 0.32 or 32%. And then the recessives is represented by Q squared. Plug in for Q. 0.8 squared is going to be 0.64, 64%. And you can always double check yourself because these numbers here should add up to what? 1, okay, or 100%. And so if I take 0.04 plus 0.32 plus 0.64, that indeed adds to 1. Yes, ma'am. So here it's saying give the frequency. I really should convert that into a percent. But yeah, if you give me a decimal form or a percentage form, just keep it consistent. Usually on the test, it'll be specific to express this as a decimal or express this as a percent. They're usually pretty good at telling you exactly how they want it expressed. Anything on number 1? And that would be sort of level 1 problem, real base level problem. Number 2, takes just another step. So it says in this case, 81% of the population is homozygous recessive. What represents homozygous recessive? Q squared. And we're not talking about the recessive allele now. We're talking about individuals that are homozygous recessive. Seeing the difference. So this is going to be, the key is Q squared is going to equal 81%, which if we put that into a decimal format, that would be 0.81. So I know Q squared is 0.81. So the simplest step to do is go ahead and solve for Q. Because if I can solve for Q, I can then solve for P. So in this case, if I want to solve for Q, I'm simply going to do what? Take the square root of both sides. Square root of Q squared is Q, and the square root of 0.81 is going to be 0.9. Okay? Therefore, P plus 0.9 equals 1, so therefore P must be 0.1. And if I lose you, don't, speak up. I can go back through it or go slower. So now that I got my values, once you know your values, the rest of it's pretty straightforward usually. So now I know the values. What's the predicted frequency of homozygous dominant? Homozygous dominant is represented by P squared. So I now know that P is 0.1 squared, and that's going to be 1%. Only 1% of the population should be homozygous dominant. What's the predicted frequency of heterozygotes? Again, if I recognize that's 2PQ, I'm just going to plug in my values of 0.1 and 0.9, and that's going to come out to 0.18 or 18%. And what is the frequency of the dominant and recessive alleles in the population? I already have my answers. The dominant is 0.1 and the recessive is 0.9. So it's just a step up. Just a step up, you had to work back just slightly. Yes, ma'am. So if I'm understanding you right, there's two types of questions they'll ask. Right? They'll ask you what's the gene frequency. And this first equation is what you need to calculate gene frequency, because that's the P and the Q value. So once you know one of those, you can easily figure out the other one. This equation here deals with genotypes. Those are genotypes. P squared is 2 P's. TQ is heterozygous. Q squared are 2 Q's. So if you're dealing with a genotype, generally you have to go to this equation first. Now, if I'm starting with a genotype like Q squared, in order to go over to the other equation and use it to figure out the frequency of the allele, I have to take the square root. Okay? If I know these values and I want to know the genotypes, now I got to plug it into. Am I making any sense there? Okay. Let's look at number 4. Is this helping or is this just a waste of time? Okay. All right. Because if it is, it's like we got it, just tell me you got it and we can go forward. I've got this great activity waiting for you. All right. If we don't get to it, you won't have anything to do tonight. 4. Okay, that is a problem. Who wants a night off? Nobody. If brown fur coloring is dominant to gray. Brown is I always like to mark things as I get them. So brown is dominant. Let's give it a big B. To gray. So I'm going to give that a little b. Or you could skip the b's and just say, well, this is going to be P then, and this is going to be Q. However you want to do it. If you have 168 brown mice in a population of 200 mice, okay, so that's the value I'm given. I got 168 brown mice out of 200. From that, I can get some type of percent. So if I take 168 divided by 200, it's about 0.84, I think. But now the key is, what does that represent? That represents the brown mice. So what value or values represent brown mice? P squared and 2PQ. Those both represent that 84%. That's not going to help me because I've got two unknown values. I don't know P and I don't know Q, so I can't solve for either one. So I got to get a number that I can get down to one unknown value. Okay? So what can I pull out of that 0.84? Absolutely. I could take 168 and subtract it from 200, which would be 32 divided by 200, and that would give me my recessives. Or I could just take 0.84 and subtract it from 100, or 1, and that would be 0.16. Either way, I'd get the same answer. Going anywhere? What represents that 0.16? Q squared. I now have how many unknown variables? Just one. I can solve for that. So now what am I going to do? Q squared equals 0.16. So how do I solve for that? Take the square root. Square root of Q squared, the square root of 0.16. That means Q equals 0.4. Yeah. Well, I got Q is 0.4. I'm probably at the point now I don't have to necessarily write it down on the piece of paper, but you should for now, just to make sure you're going through all the steps. All right. But what's P going to be? 0.6, because we in our head should be able to say P plus 0.4 equals 1, therefore P equals 0.6. I now have got both values. So what's the frequency of heterozygotes? That's 2PQ. So again, I'm going to plug in 0.6 times 0.4. That's going to be 0.48 or 48%. Of predicted frequency of homozygous dominance, that's P squared. Again, plug in 0.6 squared, 0.36, 36%. And homozygous recessive is Q squared. We already know the answer to that because we already calculated, which we know is 0.16 or 16%. 48 plus 36 plus 16 will equal 1, or 100%. Yeah? So now we try to start putting it into a more realistic situation. So it's cystic fibrosis is a genetic disorder in homozygous recessives that causes death during the teen years. If 4 in 10,000, there's my number, 4 in 10,000 newborn babies have the disease. What do you have to be to have the disease? Homorecessive, which is what value? Q squared. What are the expected frequencies of the three genotypes of newborns? Assuming the population is at Hardy-Weinberg equilibrium, which means there's no change currently going on. What is the assumption not? Why is the assumption not strictly correct? We'll come back to that one in a second. So if I take 4 divided by 10,000, I don't want to do that. Too many decimals. How much? So take the square root of both. Sure. So if you do the math, Q should equal 0.02. Therefore, P is going to be P plus 0.02 equals 1. Therefore, P will be 0.98. Now it says, what are the frequencies of the 3 different genotypes? What can I expect in this population? I can expect the following outcomes. I already know that the outcome for this is 0.00004. Very, very, very small percent of people will have it. That's 4 in 10,000. Right? The others I just plug in. So 0.98 squared would be 0.96. So I expect 96% of the population not even to carry the gene. 96% of the population would not even carry the gene. And then 2PQ, we would take 2 times 0.98 times 0.02. And that would be 0.0392. And you can see that's going to come awful close to 1. Why is this assumption strictly not correct? Why can't we assume that we're at Hardy-Weinberg equilibrium? What's that? We definitely got some natural selection going on here. The fact that these individuals typically die at a young age, there's natural selection taking place, and it's not truly at a complete equilibrium. And if they're dying as teenagers, they're missing the opportunity in most cases to do what? Reproduce and pass the gene on. So therefore it is not a true Hardy-Weinberg equilibrium. Why does it survive then? You have carriers. You have carriers who don't have the disease, but they can pass it on. Is that the last one? Yes. Okay. Oh, it's the one about the giant guinea pigs. Yeah. Okay. Well, at this point, we might as well go forward with this one first. Yes or no? You sure? And the only difference here is you got to convert the percents into real numbers. But okay. We're going to show you. You're not just trying to do the old delay tactic so you don't get the homework, huh? Okay. Year 2374. It's a little ways from now. We developed the technology to travel for time. Yeah, whatever. We want to look at extinct animals. Yeah. We go way back to Venezuela, where we see a population of fibroims, whatever, blah, 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 700-pound freaking guinea pigs. Okay. Wow. Actually, 1,500 pounds. Okay. The coat color of this rodent varies between tan, which is dominant, so I know that's going to be the p-value, and brown, which is recessive, which is going to be the q-value. Assume the population isn't Hardy-Weinberg, blah, blah, blah. You observe 336 tan giant guinea pigs and 64 brown giant guinea pigs during your study. So there's my data. 336 plus 64. Total number of guinea pigs observed, 400. Which value do I want to calculate? The recessive ones, which is what color? Brown. So to do that, Q squared is going to equal, what number represents the recessives? 64 out of 400. So if we do the math, Q squared should equal 0.16. Take the square root. Q is going to equal 0.4. And if Q equals 0.4, then P must equal 0.6. Only thing new so far is you had to add the numbers together to get the total. Ooh. Yeah? So what is the frequency of the homozygous recessive genotype? Well, we already calculated that. That's 0.16. 64 out of 400. What is the allele frequency of the dominant allele? We calculated that. That's 0.6. Of the animals you observed, how many were heterozygous? How many were heterozygous? Well, I can just plug in now. We would predict that the heterozygous should have been 2 times 0.6 times 0.4, which would be, what, 0.48, I believe? So we'd expect about 48. Okay, but it didn't ask me the frequency. It asked me how many. So how do I get the number? 0.48 times 400. 48% of those 400 guinea pigs should have been heterozygous. So 0.48 times 400 is how many? 192. Beautiful. You don't expect me to do the math for you, too. So the answer would be 192. That's the only new twist is, again, take your size of your population and multiply it by your percentage. Yeah? Well, this gives me the opportunity to give you a second. Oh, okay, I know what we can do now. All right. Don't worry, I found something for you. How many of the 650 animals would you expect to be tan? Well, tan was the dominant, is that right? So I've got to take the 0.48 from above, those are heterozygotes. I mean, I could recalculate it. You know, I'm basically going to take p squared plus 2pq. I already know 2pq from the previous problem is 0.48. So now I've got to take 0.6 squared plus that. So that's 0.36 plus 0.48. Therefore, I'd expect 84% of the 84% of that. So this is our second trip, by the way. So 84% of 650 would be what? How much? 546. Yeah? So again, we're assuming the population is still in Hardy-Weinberg equilibrium, which means we can assume the frequencies have stayed the same. We can assume the frequencies have stayed the same. How many of these tan animals are homozygous for the dominant allele? Well, that's just going to be 36%, 0.6 squared, times 650. 0.36 times 650 would be how much? 234. How many of these 650 animals would you expect to be brown, assuming the population is still at Hardy-Weinberg? So we know from the previous problem that that's 0.16 times 650, and that should be 104. Yay? Questions to this point?